Hey there, AP Pre-Calc. It's Miss Adams from Flamingo Math. Let's finish up lesson 3-5. We're in day 2, talking about period and frequency of sinusoidal functions. We'll have some graphing. We'll also have some application questions. So we've seen in the general equation y equals sine of bx or y equals cosine of bx, that b value inside the argument is what value we need to divide by in order to find the period. So it's the time per cycle to complete one cycle. The frequency, on the other hand, is the reciprocal. So that's the cycle divided by the length of time. Let's look at example 8. Use the equation to find the period and the frequency for each function. Here our b value is 1/4, so we want to do 2 pi divided by 1/4. That's going to give us the period, 8 pi. This is our period. So the frequency is 1/4 divided by 2 pi, or b divided by 2 pi, which is going to be 1/8 pi for the frequency. So you get one cycle in 8 pi time, or the period is 8 pi radian. For part B, 2 pi divided by b, the b value is 48. So 2 pi divided by 48 pi is going to be 1/24 for the period. And for the frequency, b is 48 pi divided by 2 pi. So the frequency is 24 for our frequency. Let's try this application problem next. We have a mass on a spring that oscillates back and forth and completes one cycle in 1/4 of a second. Its maximum displacement is 6 centimeters, and we want to write an equation that models the motion if the spring is released from the maximum height. Then we want to find the frequency of the behavior. So we know up here this is 6 centimeters. And we can read through the problem. This is my amplitude. So that's the A value. And the time over the cycle is 1/4 of a second, time divided by cycle. When we say we release from the maximum height, that's telling me I need to use the cosine function, since cosine starts from maximum, intercept, minimum, intercept, maximum. So starting at a maximum tells us to use cosine. So we want to model our equation as D equals A cosine BT. And we already know that A is 6. So cosine, and then we need to calculate the B value. So how are we going to get the B value? So 2 pi divided by b is 1/4 of a second. So b is 8 pi, since we know 0.25 is 1/4. So that's going to be our 8 pi t. So the displacement is in centimeters, I believe. Yes, centimeters here. And the period is 1/4. We already were told the period is 0.25 of a second, or 1/4 of a second. So our frequency is going to be, we'll get 4 cycles per second. Since we get 1 cycle in 4 seconds, we'll get 4 cycles in 1 second. That's not too bad. Example 10. Let's jump over to talk about concavity, points of inflection, and bounds. We've explored concavity and points of inflection in some of our earlier lessons, And we know that a point of inflection is going to occur where a graph changes concavity. A point of inflection occurs where a graph changes concavity. The 5 key points of a sinusoidal graph can be named as intercepts, maximum values, and minimum values. And you can also name the critical points as upper bounds, lower bounds, and equilibrium. So let's look at a practical application to consider those items. Think about the 5 key points for one period in this graph that were shown here. If you look at the graph, you can see that we start at a intercept, then a maximum, then an intercept, a minimum, and another intercept. That tells us that the period for the function stops at 2 pi over 3. That's one complete cycle right there. So we started at 0 and we completed all 5 major points between 0 and 2 pi over 3. So that's our period. Identify where the function is concave up and concave down. So for part B, our graph is concave up between pi over 3 and 2 pi over 3. This is concave up, pi over 3 to 2 pi over 3. We only use open intervals for concavity. And the graph is concave down between 0 and pi over 3. So that's concave down right here. For part C, identify the intervals where the function is increasing or decreasing. So for part C, we are increasing on the interval from 0 to pi over 6, and we're increasing on the interval from pi over 2 to 2 pi over 3. Then we are decreasing on the interval from pi over 6 to pi over 2. And then finally for part D, we want to name the points of inflection. So we have a point of inflection, 2 different places. The first one is at pi over 3, and the second one is at 2 pi over 3. We could also say there's one at 0. So 0, the graph would have started to change from concave up to concave down. And then at pi over 3, we're changing from concave down to concave up. And then again at 2 pi over 3, we're changing from concave up to concave down. And then did we need to say the period? The period was 2 pi over 3. So that's the first one. How about if you turn off the video and try B and C on your own, and then come back to check your work against my work. For the second one, we have the period is 4 pi. The 5 key points are 0, 3, pi 0, 2 pi negative 3, 3 pi 0, and 4 pi 3. The function is concave up between pi and 3 pi, concave down on 0 to pi and 3 pi to 4 pi. The graph increases between 2 pi and 4 pi, decreases between 0 and 2 pi, and has a point of inflection at pi and 3 pi. Then for part C, we have the period is 3 pi, so it takes 3 pi to complete. We have an intercept at 0, 0. 3 pi over 4 is a minimum. 3 pi over 2, 0 is an intercept. 9 pi over 4 maximum, and 3 pi 0 intercept. You're concave up from 0 to 3 pi over 2. You're concave down from 3 pi over 2 to 3 pi. Increasing from 3/4 pi to 9 pi over 4, increasing. Decreasing from 0 to 3/4 pi, and decreasing from 9 pi over 4 to 3 pi. Points of inflection are the intercepts at 0, 3 pi over 2, and 3 pi. Let's take a look at example 11. This is our last example. It's similar to a free response question. Here we have a buoy that's oscillating as waves go past. For any given time, it moves a total of 4.5 feet from its low point to its high point, and then returns to a high point every 15 seconds. So we go from low to high. That's telling us that we have 15 seconds between the high point to the next high point. That's the period there, 15 seconds. And the key points are going to be minimum intercept, maximum intercept, minimum. So we've got those key points that they've told us. We got a min, an intercept, a max, an intercept, and a min, because it's telling us here in part A, if the buoy is at its lowest point at 0, that's a minimum. We want to write an equation that models the motion of the buoy. First, let's figure out the amplitude. So we have 4.5 feet divided by 2, that's 9 over 4, and then 2 pi over b is 15 seconds. So we know that 2 pi over 15 is our b value, and our equation would be, we need to go minimum first, so the a value would have to be a negative a, and a minimum would mean a cosine function, and we'd have 2 pi over 15 for the b value times t, and that would be in feet. So we have a model that describes the behavior. What's the frequency of the motion, and explain that in context. So the frequency is 1 over 15. The frequency is 1 over 15, which is 1 cycle every 15 seconds. The buoy moves 1/15 of the pathway per second, is what that's telling us. The buoy moves 1/15 of the path per second, because we've got 15 seconds per cycle. So 15 seconds per cycle. The frequency is 1 cycle every 15 seconds. And we know that the a value had to be negative 9 over 4 to give us the low point as the first point. In part C, we want to use a graphing utility to find the point of inflection where the buoy is at its equilibrium. So I did this off to the side. I'm not going to pull up my calculator here, but I know at t equals 3.75 seconds, the buoy is at equilibrium, EQU. And the path is changing from concave up to concave down at that place. So I just want to be able to explain that, from concave up to concave down. What does equilibrium of the buoy mean in respect to the behavior of the waves? We could say the behavior of the waves at the equilibrium point means the height of overall action is at the midline of the height of the wave. So I've said that here, the behavior of the waves at the equilibrium point means the height of the overall action is at the midline of the height of the wave. And in my graph down here, you can see how that's happening. And for part E, if we want to identify the interval where the buoy is decreasing, if we started at a minimum here at 0 and went intercept, max, intercept, min, intercept, max, intercept, min, you can see the decreasing section from 7.5 seconds to 15, and then it's going to repeat itself every 15 seconds afterwards. So 22.5 seconds down to 30 is decreasing again, and that pattern is going to repeat over and over. Thank you so much for joining me for 3.5 sinusoidal functions. See you on the next lesson.